Hi linear algebra students. So in this video, I will prove the fourth property of transposes, the hardest one to prove. So watching this YouTube video and taking notes is mandatory. So I'm going to prove that the transpose of AB, like of course it assumes that A times B is defined, is B transpose times A transpose. And for this proof, I will use a little bit of notation. Whenever I write a matrix in bracket with ij, what I mean is the ij entry of A. Okay? With that taken into account, let's start the proof. So the idea of the proof is, and actually let's write it down. So the idea is to prove that the ij entry of AB transposed is equal the ij entry of B transpose A transpose. Okay, so before we start the proof, I just want to let you know that's where we are going. So in other words, step number one is to write the ij entry of AB transpose. Okay, and the first argument that we're going to use is the definition of a transpose. So by definition, so this is the row, it will become the column. Okay, so actually maybe I can color code even there a little bit. So this is the row, it will become the column. And what was in the jth column will become in the jth row. Okay, so it's the gith entry of AB. Okay, so in other words, this is just the definition of the transpose. Then from that point, what I'm using is the row column rule. So row column rule. And this is just for multiplying this thing. Okay, now here you have to be very careful. So you're going to have here A. So you're going to deal with the row J. And then with 1. Oh, that's it. Yes. So you're going to deal with, wait. Yeah, you're going to deal with row J. So which means that you're going to have AJ1, perfect, B1I. Okay, so and then what happens is that every element in the columns, in the different columns of A, you add them with the elements of the corresponding rows of B. So in other words, like you'll have 2, B2I, and then you continue like this until you hit the nth column, which will correspond to the nth row of B. Okay, so then here you have like AJ2, B2I, and then you continue like this until you reach AJN, BNI. Okay, so that is the end of step number 1. Okay, step number 2 is where I will use this notation. So we want to write what is the ij entry of B transpose A transpose. So now I'm going to use the row column rule directly. So yeah, here, row column rule. So now we have to be careful again. So that's why actually I want to write like B transpose. And then notice here that the I, so let's actually keep the same color code for you to be able to really follow what's going on. Okay, so it will be in row I, and then A transpose. okay, will be in column J. Is that it? I have to be careful. Oh, yes, that's fine. Okay, perfect. So that's it. It will be the column J. And then it's the same idea, like I1, A transpose 1J. And then you continue like that until you hit BT. So the element of the ith row and column multiplied by AT times the element of the n column and row J. All right. And now you're using the definition of a transpose at that point. Okay, so definition of transpose. So what does it mean? So instead of B transpose I1, you're gonna have here B1I. And instead of A transpose, you will have A J1. And then you continue like this until this point where you're going to have BNI. And here you're going to have AJN. And then finally, since these are numbers, you can commute the order of the products, right? So so product of number is commutative. Commutative. Okay, so this is what allows me to actually reverse their order. So I have like AJ1, B1, B1I. Then I continue like this until I have AJN, BNI. Okay, perfect. Here I have to be careful. So as you can see, you have the same thing here than what you have here. Okay. So what did we achieve? Let's erase now the idea, and let's actually erase this as well. I don't need the notation anymore. So what did we achieve? Well, we showed that the ij-10-3 of AB transpose is equal the ij-10-3 of B transpose A transpose. And the only thing you need to finish the proof is to invoke that this argument applies for every entry. So since this argument applies for every entry, it means that the matrices are equal as a whole. So it means that AB transpose is equal to B transpose A transpose. And this is what we wanted to show. All right, I hope this helped. So see you either in class or in the next video.